Hi guys, so welcome to the second lecture on the complex dynamics. We're going to pick up where we left off. And so we're going to look at some of the exercises associated with the example that I was talking about. So I'd like to begin today by talking specifically about the polynomial function Pc of z is equal to z squared plus c, with the specific case that c is equal to I over 4. So in the notation here, p I over 4 of z is equal to z squared plus c, or not c, I over 4. And if you recall last time, we had the idea that we picked a couple of points that were very close to each other, and then we saw that their orbits were very different. So if you remember, since we're brand new here, we'll recall that the orbit of a point z naught is the set of points z naught, f of z naught, f of z naught. And at some point that gets annoying to write, so we flip over to the notation, the 3 compositions of f applied to z naught, and so on. So what we've noticed about this is that very similar initial points can lead to very different behavior. And we're going to try to analyze that. So it turns out to be the case that there's this relationship between fixed points of a function and where the sort of initial points that you choose, what their behavior is. So let's calculate the fixed points. This is exercise 2 in the rotor notes. And it asks us to find the fixed points of our function. So we have pi over 4z. To be a fixed point is that the input and the output are the same. So a point is a fixed point if it gets sent to itself. If you want to think about why that's a fixed point, so we call this a fixed point, why we might use the name fixed point, because the orbit of a fixed point is not very interesting. I have z, I apply the function to it, and z comes out. I apply the function to it again, and z comes out. I apply the function again, and z comes out forever. Okay, so there's a fixed point is sort of a point that doesn't move under repeated application of our function pi over 4. So we're going to try to find the fixed points of this function. The way that we're going to do that is we're either going to run over to Mathematica to do it for us, or Wolfram Alpha, or whatever your favorite tool is, although it's instructive to try to do this by hand. We're going to write down z squared plus I over 4, and we're going to set that equal to z. So basic techniques here are things like, I don't know, I guess you could use the quadratic formula. My preference is always to complete the square. So if we set this thing up to complete the square, what we're going to find is that I think we'll put a 1/4 right here. So we get 1/4 minus I over 4. This will turn into z minus 1/2 squared. It's 1/4 minus I over 4. Hit this with the square root, and you'll end up with z is equal to 1/2 plus or minus the square root of 1/4 minus I over 4. Now this, if you like, you could write that down as a polar number and actually calculate the square root, or you could run over to Wolfram Alpha, and what you'll find is that there are 2 roots to this equation. We have, I guess the first one is that this is minus 0.05 about plus 0.288i. And there's another root which looks like 1.05 minus 0.288i. Okay, so we get our, they're not conjugate roots this time because our equation had an I in it, so be careful here. Roots don't have to be conjugate if we have polynomials that have complex coefficients. So what we want to do is we want to show that the behavior of these things is dictated by something about the function itself. So I'm going to go ahead and I'm going to call this, in keeping with the rotor notes here, I'm going to designate this with the symbol Z solid dot. And I'm going to designate the other point. Does he actually give it a name? He must. Yeah, he's going to call the other one Z star. Those are the two fixed points for the function. And the idea of this exercise is that I can predict what's happening close to each of these points by looking at the linear approximation for the function near those points. So that is to say, if you recall, in our first notes, if we had a function that looked like f of z was equal to, in fact, maybe we can go all the way further and say L of z here, L of z, which was equal to az, that when the absolute value of a was less than 1, we spiraled in to 0. And when the absolute value of a was greater than 1, we spiraled out from 0. And so the coefficient of the z term is going to dictate what the so you can think this sort of controls what's happening. Large modulus a's are going to make things move away from 0, and small modulus things are going to pull them in. So the idea here is that if we start with our function pi over 4 of z, and then we compute the linear approximation of f near z dot, and we could also compute the linear approximation of f near z star, then the coefficient of the z term should tell us if f is blowing up or shrinking in at that point. So let's do that. It's pretty easy, not so hard to believe, I think, that p prime of I over 4 at z is equal to 2z. So if I actually calculate p prime I over 4 at z dot, well, that's going to give me 2 times z dot. Of course, I know the value of z dot, which was minus 2 times minus 0.05 plus 0.288i. And so the modulus, or absolute value, of p prime of z dot at I over 4 is equal to, it's easy enough to compute, modulus of, this is about 0.58. So this is an about equals, and that's less than 1. And so what we're saying is that if I wrote down the linear approximation for this polynomial at the point z dot, then locally, by which I mean near z dot, we can imagine pi over 4 of z as sort of being about equal to 0.58 times z minus z dot. This is the structure of the linear approximation here. And yeah, so what this is telling you is that this number is less than 1. 0.58 is smaller than 1, which means near z dot, this thing is going to have the behavior of pulling points in. On the other hand, if I do the same computation, but I do it at z star, so this was smaller than 1, so what we should believe here, again, is that this is somehow, the behavior that we should anticipate is near z dot, and we anticipate spiraling in orbits. If we run the same computation, but we do it for the other point, so that is to say, we write down pi over 4 at z prime, which again is 2z, and we calculate the modulus of pi over 4 prime at z star. Well, that's the modulus of 2 times 1 point, what was it, 1.05 minus 0.288i. And if I run that calculation, what I get is about 2.2, which is to say that near z star, pi over 4 of z is about equal to 2.2 times z minus z star. Sort of a way of thinking about the linear approximation is there. I mean, there are adjustments that need to be made for the actual value of the function at those points. So to fully complete the structure of the point slope form here, I actually have to put in the value of p at z dot, and I have to put in the value of p at z star. But remember, what's controlling the behavior at that point is this chunk right here, which says that in the linear approximation that this thing is sort of, that's telling you that since the derivative is bigger than 1, point should be pushed away by that point. So near z star, we should expect points to be spiraling out or pushed away. And these things have names. So a point where we have things that spiral in is called attracting. So z dot is called an attracting fixed point. And z star is called a repelling fixed point. So of course, other behaviors are possible here. I guess I should point out that when you're looking at these things, I would like you to, if you don't want to do the epsilon delta proofs that are present in these notes, you don't have to, although they're worthwhile to think about. I will try to guide you to the exercises that I think are interesting. But the basic idea that you should be thinking here is, okay, quadratic functions generally are going to have 2 fixed points. What is the nature of those fixed points going to be? And is there some sort of prediction we can make about those fixed points on the basis of the parameter c that we chose originally? So given a value of c, we construct pc of z is equal to z squared plus c. Is there always going to be an attractive fixed point? Is it the case that, is it possible that we could have an orbit where things bounce back and forth? So that would be an orbit where we have sort of what's called a periodic cycle. And so the next example is intended to sort of reveal something about more complicated behavior that can arise. All right, for the next example, we're looking at the map PC of z, where c is equal to -1. That is, we're thinking about p of z being equal to z squared minus 1. And I've pulled over the picture from the rotor note so I can explain what's going on here. So for this one, if you seed this map with a couple of initial points, so the initial points here that we're considering are this point and this one, you can see that those points are pretty close together, and yet they seem to have pretty wildly different sort of behavior, right? So on the one hand, we have the point on the red curve, that orbit, so the red orbit looks like it's running away to infinity. So we start, we track along, W2 is down here, and then we fly away. Whereas the similarly located point that's at the blue point, so the blue orbit, looks like it's doing something periodic. So if you track what's happening with the orbit, it looks like what's happening is it's bouncing in and out, and then eventually it settles down into an orbit where it looks like it's flipping back and forth between 0 and what for all the world looks like it's converging to -1. So this looks like it's about equal to 0, and this looks like it's about equal to -1. And so it's not converging to a single point, but it looks like it's converging to something that looks like what you might think of as a periodic orbit. So we can check and see that that's the case. We can find that pretty easily what those points must be, or what that orbit actually is, because we can just do algebra, right? So if we actually keep track of what's happening, if we plugged in 0, so just imagine you started with the point 0, and then you applied z squared minus 1 to it, you would get the point -1. And then if you applied z squared minus 1 to that, you get the point 0. And if you apply the point z squared minus 1 to that, you get -1, and so on. And so we could at least make the assertion that if I start reasonably close to either one of those points, then I could be pulled into that orbit. So if this is what's called an attracting orbit, an attracting periodic orbit, and here the period would be 2, the assertion there is that points reasonably close to any point in an attracting orbit get pulled into it. Of course, that's a subtle question of what we mean by reasonably close, because there must be some sort of boundary between the places where these things get attracted into the orbit and the places where they get repelled, because as we see, the initial conditions here are just that slight variation in where we started with the blue curve and where we started with the red curve is enough to induce really different behavior. The blue curve got pulled in, and the red curve got thrown away. Okay, so that's another possible behavior. So our first possible behavior was that we had these sort of fixed points that were attracting and repelling. Our second possible behavior is that we have points where things can get pulled into attracting periodic orbits. In fact, you can think of the fixed point case here earlier as representing the case where we have an orbit of period 1. So this is a period 2 thing. And then just to exhibit the other kind of behavior that you might think about, we also have the possibility, perhaps, that there may be nothing that attracts. So let's think about the map where PC of z, where is z squared plus c, with c equal to positive 1/2. And so now the question becomes, if I write down z squared plus 1/2, does anything converge? And so what I'd invite you to do here would be to play around with some initial points and see, can you find any value of z, of z naught, so that the orbit of z0 doesn't run away to infinity. So one way of doing that would be just to calculate some iterates of this function in your favorite program or a calculator. This isn't so hard to do. And then, it's easy enough to post a Mathematica notebook on how to do this. I'll give some hints about some ways that you might approach calculating these orbits. Yeah. So that's kind of where I want to get started today, or where I want to leave off today, sort of in this exploration here, which is I'd like you to, sort of as an exercise, see if you can figure out for different values of C. So for different values of C, can you find different sorts of this behavior, of orbit behavior? That's worth playing with. And I'll post some resources that should help you do that play. All right, we'll talk to you guys soon. See you.